Good afternoon. Welcome to lecture 73 and 74 on thermodynamics of materials. We will continue with phase equilibria for single component system, and we will consider Clausius-Clapeyron equation and other related issues. So as we started, this is the phase diagram for single component system given by figure 1, and consider A is the single component. Okay, and then we are going to draw this diagram. Rather, we are going to find the equation for the equilibrium curves, namely OA prime, OB prime, and OC prime, as you see here. OA prime, OB prime, OC. These are actually solid liquid equilibrium, OA prime, liquid vapor equilibrium, OC prime, and solid vapor equilibrium, OB prime. So, as I have said already, that we are going to find the equations for these three curves so that we may draw the diagrams ourselves. Now, so first we consider solid liquid equilibrium. As we started, solid goes to liquid, which is given by the curve OA prime. Then we will pick up liquid vapor. So, start with this A solid and A liquid under equilibrium in a given temperature and pressure. See here this point. Before this, I tell you what is OA prime. These comments I made, but it is better I write them. It helps you. Remember, OA prime is actually represents the melting points. And how many melting points are there? Infinite number of melting points. So OA prime represents the locus of the melting points. And there are infinite number of melting points. But how many points are there? Each point is a melting point, and there are infinite number of melting points. Of particular importance is the melting point corresponding to 1 atmospheric pressure. So you see, it is always a pressure temperature combination. What is this point? For a certain value of P, the corresponding value of T, or conversely, corresponding to a given value of T, what is the pressure? So this is pressure temperature combination. Okay, so melting, infinite number of melting points. The melting point, particular melting point corresponding to P is 1 atmosphere is called the normal melting point. Is called the normal melting point. This point you have to note. Similarly, you can draw a line perhaps to show that. Similarly, just to paraphrase this in terms for the OC curve. Similarly, is actually liquid vapor equilibrium. OA prime is solid liquid equilibrium. OC prime is solid vapor equilibrium. I'm very sorry, liquid vapor equilibrium. Similarly, OC prime is what? Just paraphrase, represents the locus, represents the locus of the boiling points. We call it boiling points. And there are infinite number of boiling points, and there are infinite number of boiling points. Number of boiling points. And the boiling point corresponding to the boiling points, the boiling point, I'm sorry, the boiling point corresponding to P is 1 atmosphere, corresponding to P is 1 atmosphere is called normal boiling point. Is called the normal boiling point. Normal boiling point. So these are the points that I wanted to add. Similarly, OB prime, I will not write here. OB prime would be what? What is called? These are actually locus of which point? I will not write here, but you can write yourself. Or is the sublimation. Good. Solid vapor is the sublimation. And this is melting, this is vaporization, this is sublimation. So it is the locus of the sublimation points, and there are infinite number of sublimation points since the curve made up of infinite points. So is the infinite number of sublimation points. Okay, and the one that is corresponding to P1 atmosphere will be called normal sublimation point. Okay, if it's actually if it's available under 1 atmosphere. Okay, so this is the general thing that I wanted to let you know. So I start. We are actually trying to draw which curve first one by one, OA prime, and then I will take up OC prime. And OC prime and V prime similarity, solid vapor, that is liquid vapor, I will take up subsequently. So first attack solid liquid equilibrium, then we can draw the diagram ourselves. So the modest start. This is at a given temperature pressure. See, you follow this. What is the purpose? TP relation. We are going to draw the curve OA prime, means we will try to find that equation. Equation means T and P relation for the curve OA prime. So start. Thermodynamically, we will actually get this, achieve this. At equilibrium at T and P, I have written this equilibrium, first top at the TP equilibrium. For example, say P, so then delta G is 0. Delta G is 0 for equilibrium, delta G is positive for impossibility, delta G less than 0 for spontaneity. We cannot lose track of this. This is true. So delta G is 0, that means GA liquid is GA solid. Now we re-establish the equilibrium. Follow. This is 1. I can get another combination. So many, infinite number. So now let us re-establish the equilibrium. Re-establish the equilibrium at what? Change the temperature, change the pressure. This is the idea. Now, if you change only one, you will not be equilibrium anymore. Change, see, this, change one, change another. Corresponding with the compatible values. This. So, how will you call this? At generalize as T plus dt and P plus dp. Achieve, re-establish. So then what will happen? You see, there will be if we change the temperature, then what the free energy of this liquid will increase and free solids will increase. So I will say by the amount Ga plus dGa, right? This liquid L I am writing short. Ga liquid will, because as temperature increases, this gentleman will have any phase as a temperature. What is the effect of temperature? Recall that. I will ask you. I will come back to this. How much will be the change? dGa, name is dGa because I have changed the temperature. It's a strong function. Temperature, pressure will change free energy. So, but this is the difference. This is a change that has happened, and correspondingly, what has happened to other one? Ga solid goes to another. It gets an increment or change rather to this, and they must be equal. They must be equal. Why? They must be equal. Why? Okay, again equilibrium. Again equilibrium. This is the new. This is the new free energy of the liquid. This is the new free energy of the solid. And since they are in equilibrium, I have to re-establish the equilibrium. So again delta G is 0. Again this same. So from 1, call it 1, equation 1. And call it equation 2. From 1 and 2, what you get? From 1 and 2, what you get? Tell me. See, substance, DGA liquid is the change that has occurred on the liquid phase is same as the change that has occurred on the solid phase. Acha, is correct? Is easy to? It's very easy. Okay. Now one thing I tell you, A, I have said A is the component, single component. Example, iron. Metallurgist will actually like hearing iron. Then H2O is very common to every discipline, and zinc also another material, copper, tin, lead, so on. So okay, very good. Alcohol, chloroform. Okay, so like this. So this is now tell me what is this value? So very easy. See figure, what is the picture? So 1 pt equilibrium. This P and corresponding go down T, first one. Second one is a little bit above it, maybe. This corresponding this I call P plus dP, this I call T plus dP. Again, this energy of this phase and that phase will be same because this is again on this line. So DG, what is this DG? Tell me. Remember what is the reason that there is a change in energy? Because I have changed the temperature and pressure. By what amount? dP and dt. Temperature is dt increased dP. So what is the corresponding change in is dJ is effect of pressure and dP minus SDT. So let us write out VA liquid dP minus SA liquid dt for the liquid phase. Likewise for the solid phase, same. So same means VA solid dP minus SA solid, I am very sorry, SA solid dt. Now you are all set, almost close. Or just dP VA liquid, just little bit. Okay, this one is transposing VA liquid minus VA solid. We just, this is this dP side change goes to SA liquid minus SA solid. This goes to right hand side and with dt, or dP by dt is, or dP by dt is what? Which you wanted to know. SA liquid minus SA solid over VA liquid minus VA solid. Okay, this is actually, remember this is in short form. In short form I am giving you S liquid minus short, S solid, V liquid minus V solid. Right here short form. Just we omit the name A. See, this is called delta S. See, delta S liquid reaction is what? Solid to liquid. See the reaction underline. This is the reaction. This never forget. Solid to liquid. Delta S. Product minus reactant. So delta S over delta V. This is actually, so far we have reached. Now you see this represents. Please tell me what is this? This V. Delta S. This refers to which temperature? Please know. This refers to this. This means this. This refers to which? Refer to, you try to follow this. Refer to TP. See here. This means this. So S liquid or S solid refers to which temperature? This entropy is which temperature, which pressure, sir. Then you will get the entropy because it changes. Which temperature, pressure? This original one. Temperature TP. Then why the VdP? V of this at this temperature, then change in pressure dP. So V remains back there, refer back to the previous temperature T. P said V dP. So V for P, V dP for the change in pressure. And similarly, temperature S entropy for this temperature T, and effect is for the dt S T is because change in temperature. So B, this entropy, this is your like your PdV, work done PdB. P, when you change the volume dV, the P actually for the previous volume, V volume, but dV it will be PdB. P remains there for the dB change, but you cannot actually for the next change you have to change the pressure. Like you, these I often actually consider. These are interesting. What is the slope actually like this, or say velocity? The velocity V is ds dt, displacement time. So ds is v dt. So although velocity refers to actually the one, okay, so this is actually refers to the point, then you actually consider velocity is ds dt. So this, so shall I do this here? I am tireless. This is the accelerating particle. S versus this always this implication is necessary because I will soon use this, refers to Tp. Soon I will use this. T, this is actually analogy. I'll take go upstairs. Analogy. So you are asked that what is the velocity at this point? Means at this time, sir. At this location, sir. This is Howrah to Barwan. So what is the velocity? The velocity definition requires very interesting. At a point velocity. Question is at this point velocity continuously changing. So give a velocity at this point. But definition of velocity requires change in displacement. Rate of change in displacement. This is the original definition. We need another one. There is a trouble. You need another point. But each point changes. So which point you will take? Then calculus solves this by how? How? Take a point as close as possible to this. Namely dt or ds, which means tends to 0. How much it is? We cannot express this. It tends to 0. So this is actually next point. You never can show, but still you have to show. It is the dt, t plus dt, and this is s plus ds. So what is this? What is this? And velocity, as in each point, why tangent is the velocity. V is ds dt. Tangent velocity, each point changes. So what is this velocity? V is, so this is your dt, this is your ds. V is ds dt, or ds is, if you ask me what is the ds, see ds is v dt. See ds is, this is the original question here. After this there is a ds, change, but it works back. See ds is v dt, dg is v dp. So it works back to the original value. So walk back to the pt, tp. So this is my logic actually, simple logic. ds is v dt. So the velocity at this point, but although dt is actually next point, not the previous one. My question was not about this point, but this is solved by dx tends to 0. So if you have remembered this, very interesting. So always you apply this, and pdb work done, pdb also similarly I explained those things, but not bad. Because since this is critical, you don't have to, I'm not allowed to actually memorize anything. That's why I'm giving the rationality behind each. Since this is true, now may I write? So if it refers to TP, at TP, now I'm applying this. I'm taking so much trouble because this refers to TP means delta means this each TP all refers to T and P. That's the original, sorry, the original point. The next point. So at TP, what is this? Tell me, delta G is how much? Tell me. Is 0, is what? Delta H minus T, delta S. Remember, delta G, the reaction, chemical reaction, delta G is 0. What is this? Delta G is 0, a chemical, remember, treat a phase transformation process as a chemical reaction. That's another chemical reaction. This, keep it, first you actually fix in your mind, okay? This, inscribe in your mind that it is a chemical reaction we are dealing. Only outwardly look different because this side A, that side A. Other is a chemical reaction. So at TP delta G is 0, I have already written somewhere. So what is this? Delta H minus T delta S, or what is delta S is what? Repeat, at TP delta G is 0, delta H minus T. Why? Remember at the given temperature is G is H minus T S, you get this. So I should not repeat so much, okay? Delta is delta. So substitute this back into this equation. So from this, so we get, shall I write here? I write first, then I once more. Or Hence dp dt is what, right? Delta S by this famous equation is in making delta S by delta V, where delta is delta H by T delta V. This is your famous Clausius equation. I'll write on the top once more. Since these are actually no longer required, so remove this. Just like this. So I write this here. This is very important. This equation. Then we write. So that is repeating. So dp by dt is delta S by delta V is actually is delta H by T delta V is the Clausius equation. This is the famous Clausius equation. Okay. Now for applying to the solid liquid, as I started low, and then I'll apply the same for other. Applying to solid liquid equilibrium, what you get? dp by dt is what? Delta S by delta V is what? Delta H at delta S, delta H, we, right, since solid is melting, T delta V. Okay, actually this right, delta H by delta have applying to solid equilibrium is what? Actually, so I should write this here, delta H by T delta V once more. Sorry, I am repeating this thing. This is called delta H melting, and this is right temperature. Delta V is a V liquid minus V solid. Already written like this. Okay, don't worry. This part, okay, this is not so. So this is the equation. Then this is the equation. Equation. This is the equation of, okay, OA curve OA. Okay, dv. This is the equation, but will equation for the curve OA in the differential form though. OA prime. Okay. Now you see, I will tell you one thing. Here, what is the T? See, original T, the original, that is melting points. These are all melting points. T plus dt melting points. Only corresponding pressures change always. There's a certain combination. This cannot be with any other one. That's unique. This. So anyway, so dp by dt is this, the equation for the curve, and so we have been satisfied. But we want to show that this is straight line further. Note, both V liquid and V solid small. This you know. Molar volumes, both are small. This you know. And their difference is even smaller. And the difference V liquid minus V solid is even smaller. As a result, which tends to 0. Even smaller. So as a result of which dp by dt is large, and consequently, hence, if it is very small, like say tends to 0, say very small, then it will be, the result will be very large. So hence, dp by dt is large. When dp by dt is large, dt, that implies dt is small. If large means steep slope, steep. It rises steep. Large, what is the extreme value of being large? Infinity. When it is infinity, what is the curve like? TP relation like? Let us see. What is the, no problem. So what is the relation like? So you have no problem. TP extreme case. What is the P on the left hand side? No? Y axis, no, sorry. When dPdt is large, extremely large, and okay, ideally large, infinity, so then it will be like this curve. So what is dt? No change. Or change in any change in pressure, no change. So it is also steep, not exactly vertical. It cannot be. It cannot be because it is a large value. dt small. So we can consider T is essentially T is approximately a constant. Approximately. See here. See how much is increased here. Pressure this much. And what is the corresponding pressure temperature change? See this way, drop this much. And here this much. That's why it is steep. That's why it is steep. Otherwise it will be shallow. Opposite is shallow. So hence T is approximately. This is approximately constant. Underline constant. Underline approximately. So that means if it is constant, then what you get? Can I get? So you see, is constant. So this leads to form, give a name. Equation I have given any name previously. Give an equation here. This will be used every so often. Equation 1, Clausius-Clapeyron equation. This is the beginning. So this leads to form equation 1 is what? dP by dt is a, tell me, this delta H is a constant. Temperature T is a constant, it is roughly a constant, roughly. I will give a rigorous treatment. T is a constant, delta H, delta V are also constant. Delta H is constant, actually enthalpy change is a function of temperature only when delta Cp exists. If it is 0, that we will consider, and delta V molar volume change is functional, but these are so small, it's also, so we consider this delta E, so dP by dt is, writing to maintain the quantity is constant, approximate, constant. Remove these lines. One by one, go, that will go down. Is constant. Constant why? Right? Note here. Note. Delta H is not functional. Constant is not functional. Is constant. Is not function. Is not function. Is not function of temperature. That is a constant. When under, tell me, delta Cp. What is the delta Cp here? I will be very happy if you can. Delta Cp, what is the delta Cp? Cp product minus Cp there. What is the product is what? Reaction is what? Solid to liquid. Okay. What are A? A solid to A liquid. So delta Cp is what? Right? Cp A solid liquid, solid product minus reactant. Minus Cp A solid. This always same thing is approximately 0. It cannot exactly 0. And so delta B is also, and delta B is also is not, delta B is not function of temperature. I have considered because volume they change, but their difference is not function of temperature. So all are constant. The dPdt is a constant. What is the immediate conclusion? Nirjor. So we have so far term by term, no approximation. Approximation, I will admit that this is approximation. dP by dt is constant. What is your comment then about this? What is your comment? Next, what is comment? dP by dt is a constant. dy dx is a constant. What is the comment? Linearity, nothing else. Why he integrated etc. That's y is mx plus c or anything like this. But it is a constant. So that's why I have drawn it straight line. You see, these are curves. I will show you. So it is a linear behavior also. Like this, sir. Like this. So it is a linear relation. So P versus T is a linear relation. So P versus T is a linear relation. And curve A prime is a straight line. Is a straight line. Okay, approximately. Then I will show you. To satisfy you, I will give you a rigorous or say more meticulous approach, rigorous approach, rigorous proof for linearity of the curve, right? Continue, of the curve. Tell me, of the curve OA prime. Oh, I stick to this quickly. You will enjoy this. Now the main thing is over. So just see, I'm giving you dp by dt. Start over. dt by dt is what? You write this nicely. Yeah, you start from there. Delta H by T delta V, as you will always write. Okay, or dp is this is very easy for you. Delta H by delta V dt by T. Happy? As if you are not going to give any. Yeah, okay, that this. Okay, not admit any serious approximation. So dp, you are not accepting any approximation, making any approximation. So now integrate. If I integrate it between limits, I'm giving you limits. What is the p is p1, a specific value. P is p1. I'm going to generate the equation. A full straight line. This is the differential form, and this is the integrated form also, and rigorous also. P is p1, corresponding t is what? T1. Okay, and it is what? P is p. Since I have to generate the equation, generally called p. T is t. That's it. Or p minus p1. Actually, by the way, what is p1 t1? I'll give an example. Suppose I ask you iron. It's a three things I said. Iron, zinc. Iron is so famous. So let us take up iron. What is this p1 and t1? Give an example. This is a specific value. When is it? p1 t1. Specific. But p is what? P is a representative. It's a variable, sir. It represents every point. But p1 is specific, means a constant then. A specific value. But any specific value for iron, do you have any idea? Suppose I ask you, what is the p1 and t1? You already gone through this, and you know something about the iron. What is the p1 t1 value? Any idea about from the viewpoint of iron? You know one thing at least. What is the melting point? You know, normal melting point. You know what is that? 1539 degrees centigrade. Convert into Kelvin. And what is the corresponding pressure? That is a normal melting point. Again, for iron, millions and infinite number of melting points. The commonly used more often than not is the normal. So what is the pressure? 1 atmosphere and 1839 degrees. Okay. So be it. Integrate p minus p1 is. Actually, can I delta, with your permission, can I take delta H by delta V, this gentleman in the parenthesis outside? Do you have now? See, I have given some explanation there on the top. Delta H is not a function of temperature under delta Cp. That still holds. That consideration. So delta H by delta V can be taken outside. So for the same reason as above, what you get then? ln T by T1. Happy? See, again, because delta H, again for the same reason as above. For the same reason as above. For delta H, delta V, not function of temperature. So function of temperature outside, or almost. No, it is better. I consider this one. This part is over, so it is better. It's a linear approximate. You can say rigorous. This is this place you use. This place you use. Yeah. Remove this. It's clear. So start quickly. Or p minus p1 or continue. Or p minus p1 is what? Delta H by delta V ln 1 plus t minus t1 by t1. No one will object. You can say this often we do. Okay, reversible work done. Okay, greater than irreversible. Okay, remember this we did. Ln t, okay. Now delta H by delta V ln 1 plus t. T minus t on any idea? Big or small? Ln 1 plus x is an infinite series, but which can be reduced to a first two terms or one term. If it is a ln 1 plus x is small. Ln x is small. So now ln x is 1 plus x plus ln x, I am very sorry, minus x square e to the power x is ln is what? X square by 2 plus x cube by 3, not factorial, 1 plus x, okay, and so on, infinite series. So when x is small, what is the ln x? Forget. Ln x is 1 plus x. Ln x is 1 when x is small. It is ln x is. I have made a mistake here. Ln 1 plus x minus na x. There is no x minus x square by 2 plus x cube by 3. I am very sorry. Not 1. Okay. This no. Sorry. E to the power x is what? 1 plus. So ln is not. Ln is x minus x square by 2. Right. So when x is higher power will be ignored, and then it will be say decimal, then it is square. Ln x is x itself, okay, and t minus t1 is also small. Why small? Is small, is a small quantity, is a small value. Why? Yes, we are trying to give a rigorous one, but that does not mean that T1 temperature will not change much. It's a steep curve after all. So temperature will not change much. So T any value T1 will be just not much different. You change the pressure from 1 atmosphere to 2 atmosphere, melting point of iron will change theoretically. But how much it will be? Say 1539.1 maybe, 0.01 maybe. Because we have seen that it is naturally steep type. Okay, so T1 is not much, it is small. It is not, we are not ignoring this, we are keeping it, but a small quantity, a small value. So ln 1 plus x is x. So it becomes, I am giving you for sake of is x means what it is? T minus T1 by T1. Write this nicely, is delta H by delta V. First term is T1 into T. Write nicely, T1 T minus delta H by delta V. Any objection here anywhere? I don't think you have any objection. Okay. Usually tell me here what are the variables, what are the constants here in this equation? As you see, p minus p1 on this side, or which are variables? And others must be constant. If they are variable, okay, so a constant, which I have already given delta H, delta V, and now T1, the main thing I wanted to focus, T1 is a constant, it's one specific value. Specific value cannot be variable. X1 is never a variable on earth, X is. So P1, likewise P1, this is another gentleman constant. So I will remove that on the right hand side, and I am writing very tidily this one for you, into times T plus P1 minus delta H by delta V. Will you give a bracket here? So this is the required P versus T relation. Which is linear in nature, which is linear, is a straight line, it is linear in nature. Why? You see, what is this? Y is equal to, what is the slope? Y is mx plus c. And you what are doing? Side change. Okay, any difficulty? Any difficulty, Major? Is in a linear.
Formula should be ln 1 plus x.
Good boy. Right. You, thank you so much. Okay, yes. It's worthwhile. I am very sorry. Very good and very good. Thank you. This has been pointed out nicely. Yes. I was also thinking about this. ln 1 plus x. Right. I made a mistake. Sometimes this happens. See, how many times I have actually considered this relation myself. ln 1 plus x. 100%. ln 1 plus x is x minus. And this is directly. ln 1 plus x. That's why actually see ln x. There is no such thing as ln x here. Ln 1 plus. This I consider to be x small. Anyway, thank you so much. Which is linear in nature. So what is linearity? Y m x plus c. Y is mx plus c type. Are you sure convinced? Are you convinced? Therefore, what is the m? This is the slope. Slope again you consider this. This is delta v being small will be very large slope. Steep slope again all the same. So this tail line is explained by this. You can give a box. So this is your final. Concerning delta Cp, I have considered. So this is over. Solid liquid equilibrium is over. Construction of the curve OA is over. Next, I take up the liquid vapor equilibrium. Okay. Shall I? Also, by the way, now one thing in passing, note this. In passing, note in passing. No, important. Note in passing. What you note in passing? That this is what slope dp by dt is what? Please tell me. Note in passing, dp by dt is what I am writing for you once more. dp by dt is right here, yes sir, delta hm, please write. Note in passing, delta hm, write this equation, T V liquid, V solid. Please tell me it is positive or negative. Yeah, I have drawn positive, but what is the rationale being drawing positive slope? It's okay.
Sorry.
Positive or negative? Here, any clue? This is the relation. dp by dt will be positive or negative. Delta hm for the melting process. Process is what? Solid to liquid. Melting is what? Positive or negative? Enthalpy of melting always positive. Why? Enthalpy. What is this? Solid to liquid reaction is. I have removed this though. Solid to liquid enthalpy minus solid enthalpy. Liquid enthalpy is always greater because you have to put in heat to get to liquid. So enthalpy is, remember, and if for ice, actually water, ice critical. You know this latent heat of fusion. They call it, okay. So positive. What is this? V liquid minus V solid. These are what? For how many moles? These are. This refers to how many. Okay, write the reaction passing. Right here. Solid to liquid equilibrium. A solid goes to a liquid equilibrium. Tell me, here, tell me, what is this equilibrium? No, 10%. Sorry, if I forget this, what is this? Delta H is what? Is a product minus enthalpy of this minus enthalpy of that. Acha, this is for how many moles are here? Showing how many moles? Molar or extensivity whole life. How many moles? If phase transformation, you don't have to write 10 or 5 or 3 because you only want the same moles either side. It 100, and then cancel. 1, always molar. Always. So enthalpy of melting, molar enthalpy of melting to be rigorous, but whether it is, so delta Hm is positive normally, and delta V is what? Tell me, guess. Which has greater volume, liquid and solid? Liquid is so positive. So no surprise. So dp/dt is positive. So the slope is positive. So slope is positive. This is our easy understanding. Okay. This is normal consideration. This is a normal situation. This is for normal cases. This is for normal cases. Abnormal key, which one? Normal cases. Abnormal who? Abnormal for unusual cases, for abnormal cases, like cases in which I am writing V liquid is less than V solid. Then what will happen? But and delta Hm is still positive. Delta Hm is still positive. Still positive. What is dp by dt? Tell me, dp by dt. Tell me. Unusual volume of liquid is less. Is negative. Which gives this? Which system actually follows this? Water. The water abnormality is what? Ice has a actually no, smaller volume. Liquid should be better, but this is actually lighter, larger volume. Solid is lighter, volume is greater means solid is lighter, and this is denser. Okay, so volume of liquid is less, and volume of solid is greater. That's why it is lighter and floats. Okay, this is unusual. This unusual situation comes when normally this is the example, e.g. water. Water, liquid, water. Oh, sorry, it was solid to liquid. Solid is what known as what? Customer known as ice. Ice. This is water. This is water. So this is definitely negative. And what is the reason this happens? You should know this. This happens when which cases? For covalent bond. And when the solid state bonding is what is called packing is not enough. Not for metals. Metal has a good packing, close pack structure. So HCP, FCC, close pack. So in this case, don't expect. But ice is not a pack structure. Moreover, directional bond is there. What is that? Directional bond, covalent bonds. So in those cases, you expect this abnormal behavior. What happens? What's the outcome? This is happening. So TPD negative. Then what is like? What is the carb like? Yes, carb like P versus T. Tell me. Similar, this is like this, then this goes this way. Oh, sorry, sir, too much. First, this way. So this is your solid, means ice. Ice. This is your water, means liquid. This is your water vapor. Vapor. Vapor means water vapor. Water system. H system H2. System is abnormal, unusual, abnormal case. System H2. Okay, remember this. So DP is negative. So careful about this. This is actually one thing I want you to note. This is true for. This happens. This happens in case of. This happens in case of. In case of light packing, not dense, close packing, not actually. This in case of actually, in case of directional bonds, okay. In case of covalent bonds, I don't have to. I have to already mention this, so I don't have to write this. Covalent bonds or directional bonds, and packing is not close. Okay. Okay. Unlike in metals. Okay. So this part is over. Now take up the next one. Next, I start from here. Applying to, I remove all these things. I'm removing all these things. Okay, these are now make it. Just remove all these things. Sorry. Yes, it's better actually. I use my. It will be faster and more comfortable. Thank you. Here actually I made a serious mistake. Return this. Remove this. And just here. Applying to here. Yes, correct. Quickly. And very quickly. Start. I'll remove this later on. Applying to not solid liquid. What I'll apply? Tell me for this curve. Tell me liquid, vapor, equilibrium. Into liquid vapor. Oof. Applying to the equilibrium. Liquid vapor. Okay. So what is this? Liquid vapor means that is curve. Which curve? OC prime. So what is the job? Again you want to get the equation. So that you can draw yourself liquid. So that is curve. Applying to the equilibrium. Next. Applying to the liquid vapor. What will you start? dP by dt. Write nicely. dP by dt. Clausius equation. Is I am writing directly delta H by T delta V. You are all set quickly. What is the delta H here? Yes. Previous delta H was what I wrote somewhere. Delta H melting. Did I write anywhere? Delta H melting. I told perhaps. Enthalpy of melting. I said no. Yes. Delta H is delta HM because the process delta H for the reaction. Reaction is a melting process. So what's the big deal? Enthalpy of fusion or melting, whichever term you use. So delta H, what I shall write here? If it is melting there, Now it is liquid vapor, delta H of vaporization, evaporation of vaporization, enthalpy of vaporization, and T delta V also how shall I write? T delta V, V of vapor minus V of liquid. I have deleted the A, the term A actually, the name, because liquid vapor means a single component. It's okay. Now is continue. Math, simple math. What is TB vapor? Do you happy? Are you happy? Since V vapor molar volume, molar always 1 mole, phase transformation 1 mole, is much greater than. Do you agree with this though? I repeatedly emphasize this point. Okay, and that vapors we can not compare 22.4 liters second 12 cc etc. Cannot compare. So this is this, and what is this? What is this? Keep on doing yourself. V vapor molar volume 1 mole. Clear picture. 1 mole vapor. Okay. Okay. Which vapor I have considered here? Whose vapor? Whose vapor? Yeah.
Metal vapor.
Yes. This diagram for the normal diagrams. But sir, I don't maybe sir. Who knows, sir? I don't know. Say A, sir. A maybe. I maybe. So vapor. What is this vapor? What is the volume of this vapor? Is what? It will follow. We always consider ideal gas behavior. So what it will be? Ideal vapors behaving ideally is what? Ideally is what it will be? RT by. Don't you? 1 mole volume. So again back. Vapors behaving ideally. Vapors behaving ideally. And not very large pressure, and so you can expect one also. You can get ideal gas behavior. So RT by P. Why not nRT? nRT. I often insist on nRT, but I am writing RT. Any idea why I am writing RT then? 1 mole. Molar. Process is what? 1 mole liquid. A 1 mole liquid. Molar. Shall I write somewhere? Yeah. Okay. V note. V vapor is the volume of 1 mole, underline 1 mole vapor. I should write this once more. And V is a liquid also, right? Volume of 1 mole of liquid. This all molar of the reaction. Delta HB is what? Delta HB write somewhere. Delta HB is what? Tell me. I'll give you name. Delta HB is what? Molar. Good. Of vaporization. Molar. This full name. Good. Molar. Molar. Insist. Because 1 mole. You have to write 2 moles then. What's the use of this? Molar enthalpy of vaporization. Heat of. You say latent heat of vaporization. This is latent heat. You don't use the term. Molar enthalpy of vaporization. Good boy. Okay, everything is clear. So it is what? Then dP by dt, or dP by dt, continue with dP by dt, or what you are getting? dP by P. Do this. dP by P is delta HV by RT square dt. Happy? dP by P is delta H by RT square dt. This okay? Or this is also written as d ln P. d ln P is what? Delta HV by RT square dt. This is okay. Or also you can write another one, or alternatively, or dP by dt. dP by dt is delta H by RT square. I don't know which one will be required later, but this is these three actually. dP by dt is delta H by RT square. It's okay. So now or integrating. Integrate quickly. ln P is what? Minus delta HV by RT plus Z. Z is a integration constant. Z is an integration constant. Integration constant. Okay, this is the equation. So this is the equation. Box this. Acha, under what condition? Integrating means what I have considered. Tacitly, quickly, tacitly consider. Under the consideration of, tell me what I have done. What consideration I have done during integration? Left hand side, any constant. Integration. So no problem, sir. No consideration, no assumption, no nothing. The right hand side is a tricky part. So what I have considered? Under the consideration of good. Delta HV, sir. Tricky is enthalpy, sir. Not dependent on temperature. What you say? You consider. I stop for a while. Pause. Delta H, enthalpy and temperature. Oh, Kirchhoff's equation. Delta Cp. Not independent or fortunate. Delta Cp is negligible. Under the consideration, same I have already discussed. Under the consideration, delta HV is not function of temperature. That is delta Cp. Tell me, delta Cp. When it is not function of temperature, delta Cp is 0, not constant. 0. If it is constant, it is a function of temperature. That I will consider later. It does delta Cp is 0. This is okay. So this is the equation for. This is the equation for the curve. For curve, what curve? Tell me. OC prime. So you all said done. Finish. This is known as Clausius-Clapeyron equation. Now add Clapeyron. Previously it was.
Only Clausius.
Oh, Clausius, no? Check the name actually. It's serious. Clausius in mind. Clapeyron. Check. Let me check. Follow. What curve is it? This is known as, right? This is known as famous. Again famous. This is known as Clausius-Clapeyron equation. So job is in a sense over this part. This is over. But I will give you the indicator. This is actually indefinite integration. Integration alternatively integrating within limits. This you always do. Indefinite integration, definite is what? It will be what? And then you do this, start here. dln once more, right? Go back one step. Delta HV by RT square dt and integration T1 to T2, T1 to T2. I'll ask you question. See, it is customary to write this. Okay, we are actually forget about the physical significance. So what is P1 and T1? Anywhere here? Can show P1, T1 where? T2, T2 where? About this. Obviously, it will be somewhere here about this, because about this curve we are discussing, about the curve OC prime. So tell me, what is this? What can you show me what is P1 and T1 and P2 and T2? See, P1, T1 key. P1, T1 can show here P1, T1. Suppose this P1. What is P1? This point or this point? It should be on the curve. Then what is the T1? Corresponding. Infinite combinations. So P1, T1. Then P2, Ajay. P2, T2. Like this. One of them may be normal. That is up to you, sir. Above of infinity, choose one. Yes, normal. So then what will be? If it is normal, say water. What is normal? What it is? P1 is what? If it is normal, I cannot take example. We don't know vapor pressure, liquid vapor. You don't know. I also have perhaps not much about data. Water we all know. What is P1? Good boy. This is 100. Pressure 180. Right. Any other? This any value you can consider. But another is, I give you often consider this 69 degree centigrade data I gave you. You know 69 degree centigrade, it is 0.3, and also that reversal from that day. So apply. See, not when you integrate, oh, sir, like last say first year, not. So, yeah, apply. So good boy. Or ln P2 by P1 is delta HB by R minus, I write this way, minus 1 by T2 minus 1 by T1, and please box this. These are the same. This is Clausius-Clapeyron continued. The thing under definition is okay. All set to minus. Good boy. Now I tell you, similar integration you did where? I will be very happy. Similar integration already once. Exactly similar. Exactly similar once. And I in fact wanted to actually tell you whether it was covered. Then otherwise I would address this, and then later on you figure out that no, it was already covered. You showed from here. What is that? Hancock equation. The dt of ln k T2 Kt1 integration similar, and still another one will come when you study solution. This activity coefficient. So this is very common type. But anyways, now next is rigorous. Little bit rigorous. Okay. Achha. Now we consider delta Cp is 0. Achha, sir, what shall I remove this? No, I'll remove from this one dp by dt. Integration, integrating. Before this integration, I remove this. I remove this. Huh? Next, we take a more general approach. We take a more general, not fully general, more general approach about delta, about dependence, about the dependence of delta H on temperature. Or about temperature dependence on, about the dependence of, about the temperature, about the temperature dependence of delta H. Dependence of delta H. Enthalpy change. Enthalpy vaporization. Quickly, what is this? We consider, for this purpose, we consider, tell me, when you can expect delta H will be a function of temperature? When you expect delta H will be a function of temperature? When sir, delta Cp is non-zero, sir. There are how many varieties of delta Cp? 3 varieties I gave you. You know, we consider delta Cp is a constant. What is that constant? Is delta A. Delta A, remember? Delta A or A. What is the form? I tell you, Cp is A plus Bt plus 4 options for delta Cp. I give you. Recall. Remove this. This is all over though. Remove this. No way, that will not take much time. It's almost done. So delta Cp, recall. Cp is what? I give you 4 options. Cp is what? A plus Bt plus, recall Cp. In fact, it can be more terms, but 3 we at the most we consider 3. What is delta Cp? Right? Delta A plus delta B means product minus reactant. Cp is product minus reactant for the reaction. For single one, product delta B T plus delta C. I can go very fast, but give me emphasizing this. Now 4 options is what? Delta Cp having 3 terms. Delta Cp having 2 terms, 0, 1 term, constant. And then what is 4th option? First, all 3 present. First 2 present. Only first. And another is 0. This one, delta Cp is 0. I wrote somewhere. I will remove this though. So this is 4 options about delta Cp. So this I discussed in case of energy. So it's constant. So what it will be then? If you do this, Then what is delta HV? Tell me, delta HV. This one, I work on this. Delta HV temperature will be what? Tell me. I am giving you 298. I am writing. You please check. Plus delta Cp dt. Which equation? This one clearly recognize. This is, I wanted to show that there is a connection between what you have already read and what we are currently reading. Okay. This is equal to V for vaporization. V is for vapor. V for vapor. Vaporization. Enthalpy of vaporization. Okay. So what is the T concept paper? Forget T 290. Delta is T2 is delta is T1 plus delta Cp dt T1 to T2. Which equation? Kirchhoff's equation. Have you reached this? And now this time it is important. This is what? Delta H V 290. V for vaporization, molar vaporization, enthalpy of vaporization. Delta Cp I have considered delta A. Please write that. Oh, I am writing here. I am writing here. Delta is, I am saving time. Saving. Delta constant is a constant. Is a constant. T minus 298. You all set? You all set? Okay. Or this is your okay. Now substitute this gentleman where? Here in this equation. This is what temperature? Delta H refers to Tp, temperature T. But this is I am considering. Why I have considered this 298? A reference. I have to take one reference. 290 I have taken reference. I can consider 500. No problem. Say 290 is common data available. So take from this one. Okay. So I am writing this side. This side. Double star. Yeah, this side. Unnecessary. Don't go. Right. Quickly. So from here, from equation 1 to this is. Oh, since this is a very nice equation. So which one I consider as Clausius-Clapeyron equation? I have removed that. Or that is removed. No. Acha, right. Star. Double star. You can go there. Go back. DLNP is right. And I am repeating this last line. I am repeating here to maintain continuity. What is it? Delta V, what HV, what shall I write? Tell me. V, what for what temperature? Temperature T. This is for temperature TP. This is delta HV. Okay. dPdt. Remember what I told you? Delta H, delta S, or refers to TP originally. TP original one. TP. So this is what T. So the T automatic T is what replaced by this delta HV 298 plus delta nicely right. This is very easy now. RT square dt and of course integrating next. I am doing the integration, you help me. Integrating for left hand side is what? Integrating means without limits. So independent means there is a constant integration constant. Left hand side in any case LNP. First term by term see. What is this? Minus delta H by V or dt by minus 1 by T into times 1 by T. First term perfectly okay. Perfectly okay. Second term T by RT square. Take a look. T by RT square. T cancel RT. So delta A by R. I'll check if I make any mistake. Delta A by R. Oh, sorry, sir. Delta A by R. Do the integration. Delta by R 1 by LNT. A good boy. LNT minus 298 delta A. All are constant. Right, nicely. dt by R. By R. dt by T square is what? Minus 1 by T into times 1 by T. No, wrong somewhere.
So it will become plus minus plus.
Okay. Oh, this is a constant. This is another constant. They will be together. Consider. I made a mistake. It's okay. Correct 100%. But I will group them again. At the end, I have done. But it should have been done because these are constant and this is a constant. So constant one term, one constant. Okay. They are under the dt by T square. They are under dt by T square. So what it is? Right. dt by T square is minus 1 by T. Plus, na? Okay. Plus, dt by right. So please, you take the 1 by 2 together. I wasted one line actually. I am wasting one line. So what is this? Let me write correctly. Delta HB minus 298 delta A, I hope this will be correct, by R. Please, do you see this? Hey, please, do you see this line on the screen?
Yes, yes.
Yes, okay, thank you so much. Thank you so much. I wanted to write here. Minus 1 by R, huh? Minus delta, then what you write? 1 by T, na? Times 1 by T. Times 1 by T. Plus delta A by R ln T, plus here I have missed what? What I have missed here? Integration constant. Z is integration constant. Integration constant. So plus Z. Please box ln P is. This is more rigorous than the first one. First one is also in the different, moreover that is differential form. Integrated form I gave, between limits I gave though. But this is the equation P versus T relation. Shall I? It's okay. This is the shall I write? What shall I write? Okay, I'm this. Yeah, double star, na? Double star. This is the I'm removing this one. This is unnecessary now. I'm writing. Double star. One important thing I will write here. This is the equation PT relation. This is the equation PT relation. PT relation. Tell me. Fill in. This is a PT relation for the curve. What curve? OC prime. For the curve OC prime. What does it mean? Is it a, what you say? See what type of equation? LNP is this. Means non-linear, sir. Non-linear, see, non-linear. Which is non-linear. Which is, right, non-linear. So you all set. Similarly, I will not do this. Similarly, OP prime. Actually, I will check only this. I have correctly got this or not. Hope I have done correctly. This actually, since it is so many, the LNP is minus delta H. Oh, one thing I missed here, you should note this. Delta HB is okay, everything is okay. Delta A, R 1 by T, A by R ln T, is everything is okay. Only thing, what I missed here, guess? 298, when I integrated here, what I missed? 29 subscript. This is very important. This is not general, this is a specific reference I have considered. 298. So 298 you have to, do you have space? This is, I'm writing here, and this is right. Write this. Delta HV, it will be covered. So similarly, you write here. Though this is really not enough space, but I will write. Oh, sorry, I will manage it. 298 minus. Okay. What was at the beginning? Minus was there. Tell me, what was there? What minus was there in bracket? It was a bracket, and minus was there, no? It's a minus, yes, clearly it is. There 298 and minus common, minus plus. It's okay. It's okay though. So this is the equation for PT relation for the curve OC prime, which is non-linear. Okay. For similarly, we will have, I will not okay, unnecessarily take up this. Similarly, right here, okay, right here. Similarly, we can generate. Similarly, we can consider. What you consider? What is remaining? Solid vapor. So similarly we can consider the equilibrium. We can consider equilibrium solid to vapor. A solid to a vapor, represented by the curve. All right, represented by the curve. Same. I will not take up this. By the curve, by curve OB prime. So exactly similar way, exactly similar treatment, exactly similar treatment, and result is also similar. Only delta HV will be replaced by what? Guess. Delta H will be replaced by the sublimation delta HS. Only, let me write, only delta HV will be replaced by, remove this, all this remove, replaced by delta H sublimation. That's it. So here I draw a line. But there are other discussions here. Okay, is it okay? Over this part, anything else here? Not so important. So remove this. Clausius-Clapeyron part is over. You don't have to perhaps come back to this. But some interesting issues are coming. Acha. What is it? Effect next. But Clausius equation I retain this. Next, consider the effect of pressure on vapor pressure. Pressure on vapor pressure of solids, solid or liquid, of solids or liquids, all liquids. This is an interesting discussion. This I will take up this, okay, one by one. If I made a mistake, quickly. Acha. Time how much? Time how much? 10. It has. Now this is important. Effect of pressure. The effect of pressure on vapor pressure. So you see, so dg, I'm writing start this way. dg of a liquid, say dg liquid is what? dg liquid is what? We write this what? V dp under constant temperature. Achha, right? Under constant temperature. Under constant temperature. Effect of pressure on under constant. Achha, right. Something right also. Under constant temperature, right? Liquids under constant temperature. That's why you see suddenly you're considering. We know what the effect of temperature. We know. The effect of temperature you can see vapor pressure. Okay, under constant temperature. Okay. Note this effect is small. The effect of pressure is the influence of pressure, although very small. The influence of pressure although is small, its study is very important. Its study is immensely important. For concept purpose. But this is actually note. Note this. Right. Start. I am considering liquid, vapor, solid, vapor pressure. This line you consider this. Okay. Solid. Achha, good boy. Achha, what is this curve then? Liquid vapor equilibrium. What does it mean? What is the vapor pressure of this liquid? What will answer? Sir, Give me temperature, I'll give you the vapor pressure. What is this? At this temperature, this is the vapor pressure. At this time, this is vapor. Acha. Note, very important. Remove all these things. Acha, note, before I start this, note one serious, one very important point. I'm coming to this. This is important also. I don't know which which I missed. P in the PT diagram, in the PT phase diagram, which is the phase diagram, in the PT diagram, figure 1, this is very important, the PT diagram. In the PT diagram, Y, P on the Y axis represents what? I'm asking first. Represents what pressure? What pressure? Whose pressure? See, answer is this. Answer, P is the total pressure. P is the total pressure. Total pressure. Okay. Total pressure for all three cups. For all three cups. But all three cups. However, P is also the vapor pressure. P is also the vapor pressure, total pressure. External pressure. I'm very sorry. P is the external. Change. External pressure for all three curves. However, P is also the vapor pressure for liquid vapor and solid vapor equilibrium. For liquid vapor and solid vapor. Liquid vapor means what is this curve? Liquid vapor is OC prime, and solid vapor. What is this? OB prime equilibrium. Please note this. This is very important concept and it will remove your confusion. Otherwise, okay. Temperature, no problem. Temperature is temperature. Okay. Now I will take up this. I will explain this. This is the external pressure, all three external. But simultaneously, it is also vapor pressure. Vapor pressure. What is the pressure? Vapor pressure. Sir, refer to this curve. This temperature. This is the vapor pressure. What is the external pressure? Then the same. For example, 69 degrees centigrade water. 69 water. What is the vapor pressure? 0.3. 0.3 vapor pressure. What is the total pressure? External pressure 0.3. Remember that one, that figure. But this will not apply here. In the solid liquid cup, this I will show you. Okay. This also similar to this. This I am not questioning. Okay. So this I will show you. Okay. I'll show you since I in case I'm drawing this the reversible expansion of water. Okay. Water liquid. Water liquid or water vapor. This is water liquid. Water liquid. Achha, it is better I write outside. This is water liquid. This is water vapor. This is the cylinder piston arrangement. What is this vapor pressure? Okay, this is temperature is thermostated 342, 69 degrees centigrade. 69, 70 and 240, 342 Kelvin. So what is the vapor pressure? Follow this. What is the P? External pressure is what? What is the vapor pressure? Right? PH2O. Is what? How much? 0.3 atmosphere. And what is this? P external is, this is the picture. This is the picture. Okay. Then I will actually, this cylinder piston. Bad way of writing. But this I will show you actually, there is discussion later. If I retain that one, I will risk it for the timing. Okay. But this will not apply here. What is the vapor pressure? Solid have vapor pressure, but what is the vapor? I am giving an indication of confusion. What is the vapor, sir? Why is there no vapor pressure? Then how it is shown? Like these questions will come. So external pressure and will come into. So what is this? For concept purposes. Follow this. DG solid or liquid? I am considering DG liquid. Start. DG liquid is what? Is what? Effect of pressure? Tell me. V liquid is what? DG liquid is VD liquid. What else it is? Tell me. Recall. Effect of fugacity beginning. DG liquid. What are you doing? Why DG suddenly I am writing? Oh, I cannot write. What is the consideration that I am considering? I am changing free energy. Pressure changing. Free energy will change. Temperature, free energy will change. In which manner for pressure? VDP is our only answer. Nothing else. For liquid, you have taken certain amount of liquid. What is the change in pressure of free energy? This only gives, no one else. Yes, right. Is what? This is right answer. ITDNF. Right. That. Tell me, liquid. Then liquid, what we write? We cannot stay there long. What we write? RTDLNF. Liquid to liquid as the same is actually liquid is actually nothing but accompanying vapor. Same. And then further simplification is what? Tell me. Fugacity of a vapor is nothing but is pressure of vapor, because fugacities are normal and low pressure. There is no difference between fugacity and pressure, ideal behavior. So this is RT. This is actually this is the vapor pressure, right? This is the vapor pressure. Follow, please follow. What I am writing, I am changing the pressure. So I am trying to study this. So what shall I first line this? But these we have already considered. BDP, because it doesn't follow ideal gas equation. So RTDLNF. They are not okay. And again molar, recall these all molar. Okay, molar. Never forget. That's why one no NRT. RTDNF. Then fugacity of liquid is nothing but fugacity of vapor. This was established. Okay, at equilibrium. Fugacity of liquid is fugacity of vapor, and then fugacity of vapor is partial pressure. Pressure of vapor, which is vapor pressure, is because for low values, fugacity and pressure same. This I showed. No? Real gases tends to behave ideally at low pressures. So I have got this. These are the consequences. Now apply pressure. DG. DG is okay. So or VDP. I'm doing this. VDP effect of pressure on vapor pressure. So this you pick up this one. So whose vapor pressure is that? Right. VDP and be liquid. Right. Be liquid. Then it will be what? RTDLP. This is the liquid vapor pressure of the liquid, right? Vapor pressure of the. I am writing vapor pressure of the liquid. I am writing here, liquid vapor pressure. Vapor pressure of liquid vapor pressure. Is clear? See, liquid vapor pressure. Okay. It's a liquid vapor pressure. It's a this figure, liquid vapor pressure. Oh, I am telling you. What I am doing. See, this is the vapor pressure, though. If I increase this pressure, what was the pressure? What was the value at which pressure this holds? This vapor holds the same pressure as the vapor pressure. Now I increase the pressure. Higher. The moment higher it is, you may argue, sir, there is no vapor at all. Any pressure greater than this will collapse the vapor and you land into the liquid phase. The question is that the vapor pressure will increase. But since the external pressure is greater, that's why it collapses. But the question is that whether we get single phase, that is phase rule, we consider all these things. But only thing is this value of vapor pressure. If the vapor pressure value, external pressure exceeds the vapor pressure value, then vapor will collapse into the liquid. No point, no difficulty. But value of vapor pressure will it remain same? So 0.3 or 0.3 will it remain if it is exposed to 1 atmosphere? Yes. Moreover, I can show you yes, vapor exists at high pressure. But how we apply the pressure? This is very interesting discussion coming. How to apply the pressure? All the time it is there. So only thing is will it remain at 0.3 if it is when it is at an external pressure of 0.3 atmosphere itself, and compared to this when you apply a pressure of 1 atmosphere by some means, yeah, I am giving you argon. I'll give. And argon make a 1 atmosphere. Now there is no question of any collapse. Okay, this I will discuss actually. So I'm trying to mathematical. The difficulty of understanding a subject when you are carried by the mathematical relations, derivations, deduction, meaningless, all meaningless. Suddenly, DG is right. Why you are right? What is your job? So, so this increase this. Then will it remain at 0.3? Say 1 atmosphere, sir. It is 0.3 though. No, sir, I am applying sir 0.7 atmosphere. What is the behavior pressure? Will it remain at 0.3? Or say 1 atmosphere I will make. Or 3 atmosphere I will make. Will it remain 0.3? No, it increase. How much increase? Effect is very small. Concept is heavy. Without this concept, you have no comment on this. I don't know how many books have written this line. This line. How many books? I don't know. I'm not come across this. Unless this is known, student will never follow. It's okay though. Then this is the liquid vapor pressure. I have understood though. Because I am constantly liquid. If it means this cup, if it is solid, which cup? This one. This temperature, this vapor pressure. Solid also vapor pressure. Only small only. Vapor pressures. So VDP now integrate. Now we integrate, entitled to integrate from what external pressure P1 to P2 external. Okay, external pressure, and corresponding change is what? Tell me, vapor pressure. P1 I'm writing. P1 lowercase. P2 I'm writing you. P1, P2 are external pressures, and P1's lowercase P1, P2 are the corresponding vapor pressures. I'm switching from one pressure to another. Vapor pressure. For which phase? Liquid or so liquid is considered, solid is similar. It's a similar cup. Similar, everything similar. Everything is similar. Solid is similar. So one you follow, another you don't have to. Same. Have I put the question correctly? Again, in the language of this figure, using this figure or this, okay, in terms of this figure. What is this P1? Say, take an example. And also I give you, what is P1 here? Sir, 0.3. What is lowercase P1? Sir, 0.3. Vapor pressure is external. Now, P2 is, sir, it tell anything? The 10 and also 10. Make 10, not 1 or like this, 10. Now, what is this P2? Sir, it is, we do not know. It is just change. It is not 0.3, maybe 0.4. Who knows? That mathematical derivation is required. See my point? Clear though? This is a question here. You don't see here, okay? But why you say at higher pressure, you will liquid, this I have already given some outline. With argon I will make the pressure. Okay, don't worry. And then why it will be there? Not okay, etc. Many questions are there. Phase rule is coming also. Quickly. So this is none, it's over. Can I take to the outside? Think about it. You think, then you allow me, otherwise you don't allow me. Can I take RT outside? Why I can? At a given temperature? Oh, please. A B liquid, why? Sir, volume is not so sensitive to pressure, sir. From the effect of not enthalpy is not so sensitive to pressure. So many things are there. Or liquid P2 minus P1, it is one line derivation, though RT ln P2 by P1. Will you box this by all means? This is your answer. Please, this is your answer. Over. Don't you have the answer? Will you be able to give me the answer? Say 0.3. See, when it is 0.3. Okay. So when it is 10, P2 is what? Achha, I am giving in terms of the figure 2. Here figure 2. Achha, in terms of your concept fully clear. It is so much confusion. In terms of figure 2, please apply. Tell me, question you like. B liquid, is it difficult for you? I'm coming. If it is difficult, I'll ask you what is B liquid. I'll ask you, don't worry. P2 is what? First P1 is what, which you know? Tell me. This is a one case, case 1, state 1 case. Okay, P1 is Good boy. 0.3 itself. P2 is the pressure that I have chosen. So effective pressure, 10 atmosphere. 10 atmosphere. P2 is 10 atmosphere. What is the vapor pressure? Good. Is RT. R you know? You know RT, na? You know R. Is, so yeah, RT. I'm right, RT. Okay. What temperature? Right. RT is what? 0.082 liter atmosphere. Huh? Liter, 0.082 liter atmosphere, etc. Per mole Kelvin. Okay. Don't worry. T is what? T, tell T is what? The temperature is it 342. ln P2 by P1. Tell me, what is this? P2 is what? P1 is what? P1 you know. Vapor pressure. These are vapor pressures. What is this? 0.3 itself. And P2 is unknown. P2 is what? What? This is the question. Is it difficult? See, everything is known and knowables. What is not known? This is about what? Which system? Water system? What is this value? Answer this simple question. Though I would like to ask you simple question to alert you and to actually know to keep you awake. Actually, V liquid. Tell me what is the value? Liquid is being water. Water. What is the V liquid? What is this? 1 mole of liquid volume, sir. Molar volume of liquid. Not difficult at all. When they say molar, they say, oh, what is going on? Molar volume of 1 mole of liquid. How much it is? 1 mole of liquid. What is the volume? Yes, Nirjal? Gas. That's why I always ask. Water. 1 mole is 18 gram. What is the volume? 18 gram, 18 cc. Density being 1. 18 cc. Sir, can't you answer? 18. Since it is 18, so you make it 82 cc also. 82 cc atmosphere. Mole Kelvin. And I give you the value is what? What? Say 1 mole means 18 cc. 18 cc. And this is 10 atmosphere. Question. Atmosphere. These are atmosphere. Question was I should have given the question was, you formulated the question. What is the question was? Find the vapor pressure of water at, so yeah, formulate the question. I'm writing. Question was, find the vapor pressure mole Kelvin. Since I've already written, vapor pressure of water at 342 Kelvin. Oh, sorry, sir. At 342 Kelvin and tell me now, and 10 atmosphere external pressure. External effect of. Right here. Now consider effect of pressure to. Right. Effect of pressure right here. External, right in bracket here. Consider the effect of pressure on vapor pressure, those loosely speaking, but to be regarded as external pressure. Here you will try to see for solid liquid curve for vapor pressure. External vapor pressure of vapor pressure also. Okay, please. Note the influence of pressure, although small. How much answer you expect? Me say 10 atmosphere, 0.3, 10. How much it will be? Yes, I can give an answer. It was 0.3. It was 0.32. Effect is small. Concept is heavy. 0.32. But still we study. Otherwise, we will not explain these curves. You will soon see how much deep is thermodynamics and still how much consistent ever. So, effect is small. How is it small? Such a small? How do you know? Who is responsible for this small value? Who is responsible? Who is responsible for this value? Okay, you know. This is 82 cc. Who? Molar volume is so poor. Molar liquids, solid liquid have a poor molar volume compared to gases. So small, the effect will be very small. It's a log term. So this is the main reason. Okay. Good boy. Okay. This I wanted to retain somewhere. This is I've already explained this. I remove this. I want to retain because I will actually explain it. Remember. V liquid, just repeat this. So save this line. P liquid times P2 minus P1 is RT ln P2 by P1 for solids, for liquid, for effect of external pressure on vapor pressure, of liquid. Another item is what? Who is there? Vapor pressure. Whose? The term vapor pressure applies to whom? Solid, liquid. Solid vapor pressure, liquid vapor, solid vapor pressure. Sublimation point is a solid vapor pressure. And similarly, you save this. I am just writing this in case you have difficulty. I am trying to sort it. Be solid. P2 minus P1 RT ln P2 by P1. My point. These two save this. You save. This is for effect of P external on Vp of solids. Sort. Over. Next take up. If written as much as possible, these diagrams, okay? This I have saved, so no problem. Now you please follow this. Effect of this, okay? To? By the letter, I'm always constantly checking you. Whether it is 0.3, it is 0.3 here. No, sir, this is water. For what are this data? Ice, no, we don't know. For ice about this car. Oh, where did you get this, sir? Next. Now, free energy next. Free energy interpretation of melting point. Free energy interpretation of melting point. Next, free energy interpretation of melting point. I see. You consider this, okay, in the PT diagram. P is the external pressure. This I don't want to disturb. I will show you. Free energy interpretation of melting point is what? First of all, next this topic. What is the thermodynamic interpretation? Thermodynamic interpretation. Oh, again, interpretation of the statement. Let us walk this way. Of the statement, melting point of normal melting point of statement is the under quotes. The normal melting point of what is this, sir? Please. Normal melting point of iron. You are very interested. Is what? Tell me how much? 15, 39 degrees centigrade. So is Kelvin is how much? 1812 Kelvin. Check this. Is Kelvin. What is the statement is over? This is the statement. Normal melting point of iron is what is the thermodynamic statement? Melting point. You will say what? Your statement will be this, that free energy of the iron. This is the melting point. Free energy of iron solid is equal to the free energy of iron liquid at what? At this temperature and one atmosphere pressure, normal pressure, temperature. Exact temperature, pressure. The moment you drift, you will see it is not the equilibrium, it is not the melting point, it is the coexistence. These are the melting point. This is not the melting point. This is not, see, here, you see, hello. This is not this point is a melting point. This is not a melting point. This is neither this. See, this is not here, single phase. Melting point means coexistence. Solid liquid. Here, single. Then again you can change the temperature. Yes, again, re-establish. Like this, randomly play. So please follow this. So write at significant answer. At free energy, molar free energy, right? Answer. The molar free energy of solid iron is equals to the molar free energy of liquid iron at the beginning. I should have written this, but I'm writing at the end, at 1812 Kelvin and 1 atmosphere. Is okay to? Good boy, huh? It's okay to? At 18 Kelvin, huh? At 1 Kelvin. This is the significance of this. Okay. See, if you change this, say 1800, suppose this is 1800 Kelvin and this is 1 atmosphere, then what will happen? You have not coexistence of this. Okay, don't worry this point. Sorry, I will show you actually with the figure. Now I will draw the figure. This part, if you have, let me draw the figure nicely. Then I will show you the meaning of this. How you will get this? I am drawing this diagram. Okay. Again, solid, liquid, vapor. Okay. Liquid here, right here, liquid here, vapor here, solid here. Huh? I tell you one thing. What is at this point? This is your P versus T. You follow this. You consider these 2 points. P is 1 atmosphere, say. This is 1 atmosphere curve. 1. This is P is 1 atmosphere. Sorry, go slowly. Unnecessary. You will not, unless you understand, then no meaning of this class. Follow this. Follow this. Huh? Follow this. This is the melting point. One atmosphere. Okay, I'm very sorry. I'm very sorry. This is actually, I have to somehow be at 1 atmosphere right here. It is better I write close to this 1 atmosphere. And this is not the melting point. I call this temperature T1. Okay. Acha, this I call this point X. Acha, let me draw this first of all. I call this point Y, where they meet. Y. At X. X is what, by the way? At X. Then I will increase the pressure. Okay. At point X. Tell me, what happens to free energetically? Which phase is stable at point X? Where point X is, melting point I have not given, this is temperature T1. Okay, T1 I have given, and 1 atmosphere I have given. What is the significance of at point X? Which phase is stable? Liquid. What does it mean? At point X, tell me, G of liquid is stable. Stable means lower free energy, means delta G is negative, G liquid 2 is less than G solid. Please follow this. Follow with me, okay? I'm drawing you in case it is required. This is the TM. Please follow with me. This is melting point on the curve, melting point on the curve. What is the significance here? What is this? You tell me. GL is at point X. Coming point X means corresponding to corresponding temperature T1. Right? At point X, right here, corresponding to right here, point X, right here. Right point X, right here. What? Temperature T1 and pressure 1 atmosphere. Pressure 1 atmosphere. Temperature T1 and pressure 1. This is point X. At point X, pressure 1 atmosphere. So slowly. What is you got this? GL less than GS. But tell me before this, at this point, call it Z. Just I'm giving this point Z. At point Z, what is I'm not writing. At point Z, what is easy for you to write? What is at point Z? What is the conclusion? Free energy is on the melting point curve. Free energy of liquid is GL is GS. GL is GS. But at the point X, GL is less than GS. That's why consider solid to liquid transformation. Okay, if you consider solid to liquid transformation has occurred. Okay, liquid stable to solid to liquid. They follow delta G. Delta G is what? Delta G is delta G0 is what is this? G0 liquid. I'm telling you minus G0 solid. It comes in which form? Phase transformation whatever A plus BT. A plus BT form always chemical reaction. A plus BT. You please follow this. A plus BT. Please follow. This is data available. So I follow this. Now you get GL is less than GS. Why this happens? It substitutes the temperature. The A plus BT available, data available. You substitute temperature Tn. What you will get? Delta G will turn out to be negative. Negative means product is less. So GL is less. Okay. That is GL 0. Why 0? Tell me, answer this first of all. Answer this. Why suddenly GL 0? Because it is what? Pressure? 1 atmosphere pressure. So it is standard state. Pure state, they are always pure, and 1 atmosphere, this is a reference standard state. That is right. What is this? Delta G0. Solid to liquid. Solid to liquid, right? Negative. Okay. Is negative. What does it mean? G0L minus G0 is negative. That means which is greater? G0 is G is greater. So that's why what you are getting here. What you are getting? Tell me why you get what you are getting. Who is stable here from this? Higher energy, lower energy, coexisting same. And lower energy because you consider this way. Since you are interested in this type of things, delta G or delta G is delta G at this temperature. Delta G follow this. Delta G0 is delta G. So solid will go to liquid. The consideration is solid to liquid is negative. Means it will spontaneously. It is spontaneous process and liquid will be stable. So delta G0 is negative and delta G is delta G0. Okay, here delta G is delta G0 because they are standard states. Delta G is negative, spontaneous. So liquid is stable. So many ways, follow. Many ways you tell. What is the meaning of this? Sir, one meaning, quick meaning. Sir, X at point X, liquid free energy is greater less than molar implied. Liquid free energy is greater than less than solid free energy, or solid free energy is greater than that. Or in other words, if you consider the solid liquid equilibrium, delta G, which is equal to delta G0 because their standard state is nothing but negative. Same statement, solid to liquid means what? What does it mean? Solid to liquid, how do you decipher this? How do you write this? Arrow, you want to avoid arrow. What do you? G0L minus products you have. G0L minus, I'm writing you. I'm trying utmost. G0 solid. Now see, it is negative means this coming. It is negative means G0L is GL0 is just less than. So lower energy is stable. Yes, sir. Okay. This can be explained also. So it is the beginning point. End point is this. It is this. Then, so you see, there is actually equality is disrupted. Equality was here. Follow. See, logic. See what I am trying to get at. Equality was there. Equality without changing pressure, changing the temperature. No disruption. One is stable, liquid here. Can we actually get them together again at equilibrium? Then you have to do one thing, sir. If you don't, at this temperature pressure combination, you never will get. At 1 atmosphere T1, they will never be together. What is the way to get them together? At this temperature, sir, change the to compatible pressure. What is the pressure? Go up. Alright, this pressure. At this pressure, what will happen? The pressure has increased from 1 to a higher value. Say 10 atmosphere, 100 atmosphere, 300. What will be? Again, free energy of liquid will be free energy of solid. See, so every point free energy of liquid is free energy solid. So, and outside, no. Outside, this side is what? Which has greater free energy? This side, which has greater free energy? Liquid. Compared to solid liquid, this side, that's why solid is lower. So delta G negative, apply one rule. Delta G negative. Suddenly someone will say minimum, etc., etc. Don't. So this, please, this is okay though. So I want to tell what is the pressure that you will get them together. So this I will show you. I am removing this and this part is over. So please follow. So keeping the temperature fixed, I am increasing the pressure. So at pressure OI, at OI, which is what? Temperature what? Temperature unchanged. T1 unchanged. But pressure increased from tell me what? Tell me from what? It's a 1 atmosphere. This is the say incompatible. You say, sir, this is compatible. This is incompatible. So increase from 1 atmosphere to P1 atmosphere. Call this, what is this? What is this? You call this value P1. Please follow this. This is one. This one. Remove this. These are all previous lines interfering. It's okay though. It's a good. Okay. X and Y. Two things. X and Y. X is here somewhere between, landing between the single phase region. So X to Y, moving to Y. I'm getting them together. Another combination. So how will you get this value? Now tell me. So temperature fixed, pressure increasing. How the free energy of see here. They are same, sir. They are these values. At X, this is so GL0. So both will have a change in free energy. So one by one, liquid side first attack, liquid side. GL0, it was GL0. Here it was GL0. Recognize this GL0 standard state. Temperature has no standard. Any temperature at temperature of interest. So 1 and pure. So both conditions. So GL0, then it increased to which value? To higher value. What value it is? How to get that value? What I have done? It was GL0 here, but here it is will be effect of pressure on free energy. What is that? VDP. Only VDP, sir. Only VDP will explain the increase in free energy. Plus VL dP increase from what to what? Tell me. 1 atmosphere to good boy. And other side, I'm writing. I'm actually forestalling the result that it will be same. Actually, I know, but I will explain you why justification. But you write the right hand side, solid also another thing. Both. Okay. There was a mismatch. With this mismatch, one is lower, another is upper. Both are treated with the same increase in pressure. And let us see what magic happens. G0 solid. Plus what will happen? Again, this also undergo change in free energy, or how? What is the what value by which factor? Same VDP. Effect of pressure on temperature unchanged though. If temperature changes, then what will be the result? What will be the expression? VDP minus SDT. Only temperature minus SDT. VDP no. Now you yourself answer me. Can you justify? Recall GL0. How to justify this equality? Apparently, or say, okay, qualitatively, how to justify this equality? I am saying this equal. Suppose you accept, first of all, accept these are equal. That means what will happen? They will be together. They will be on the cup. There will be that will be another melting point. And solid liquid coexist. This is a melting point, coexist at this point. Happy though. So so how to justify this? Tell me. See, look, which are less? GL0 less than G0S. This part I'm writing most of the things already. Most of the discussion are based on the previous knowledge. The only thing we lose track of the knowledge actually. That is the now can you justify? This is less than this. How they can be equal? Yes, limits are same. How? Explain. Answer me. Good boy. Yes, in the line. DL and BS are different. But not only different, but which is greater? You can guess. You know that. BL is like this type of diagram, BL is greater. It is not abnormal diagram, it is normal diagram. So BL is greater, so it will have a better pickup, better increase. Lower value, started lower but better increase. Higher, less increase, and reach at the same point of Gibbs energy, and this is the reason. Okay. Yes. And writing here, you write VL dp. I'm to writing all the things. P1 is what? Greater than Vs dp 1 to P1. Hence the justification. This justifies. So one is less. So when you combine them, the same result. That will be. Okay? So this is the justification writing. So you understand this is, justification is over. Self-explanatory. Another way, can I have 5 minutes more? 5 to 10 minutes? We have over. Oh, still it is continuing. That's why I'm continuing. Achha, if I cannot run to at least time, okay, let me maybe next day. This is very important. Another very important. 1 minute though. Very important. I'm not writing then. See, this is one way of interpretation, thermodynamic interpretation of melting point. I don't melting point. Another is Gibbs. You said Gibbs energy are equal at that temperature pressure. Any other? You should note that. The answer is vapor pressure. In terms of vapor pressure, can you tell me what is that? This is tricky. So I will not. This discussion is very important. Tell me. Tell me what is this? Vapor pressure is what will you answer? Sir, I am giving you the answer. Sir, yes. In the language of vapor pressure, not free energy anymore. Language of vapor pressure. What is the significance of melting point?
At this particular
Temperature and pressure. At the particular temperature pressure.
vapor pressure of liquid is equal to vapor pressure of solid.
Solid. But where is the vapor? Yes, accepting. I'm not writing anything. So I'm showing. I'm going to give you what are going to be discussed next class. So ito same. So same say 0.003 atmosphere randomly. I don't. Even more, even less. 10 to the minus 3 atmosphere. Okay. Now what is that? Why is that pressure? It is only solid liquid coexisting. Solid liquid coexisting. What is the vapor pressure? Why you don't see? Answer is this pressure is this at this pressure, which is maybe 10 atmosphere, 1 atmosphere, much greater than simply greater than the 0.003 vapor pressure. So collapse. So you don't see. You will never see. Hope to see the vapor here, but they are based on vapor pressure. So where is the vapor there? You don't see vapor pressure. So, but there is a way to show the vapor pressure by the presence of argon. That's different issue. So but there is one point where you can see. You can see vapor also. Can you show me here? I say see the external pressure, all cases greater than the vapor pressure. Same, no denying. Solid vapor pressure is the thermodynamic statement. Because why? Then I'm writing and giving another. Gibbs energy, fugacity, activity, and vapor pressure. These are, I wrote it today on places at the beginning. Gibbs energy, Gibbs free energy, DG is, didn't I write once? Gibbs free energy, then fugacity. DG is activity, fugacity, then activity or vapor pressure. These four are interrelated. So free energy same. Now what is the other language? Other way? Vapor pressure same, as you have said, vapor pressure same. But question, why is the vapor pressure? I don't see. Because answer is, since the external pressure is much greater. At that external pressure, they are same. Okay, exactly that. But question, is there any situation here in this curve that here vapor are observable?